Hello, everybody. I'm back with another problem related to the subject of statics and topic of rigid body equilibrium. And it's a two-dimensional situation, two-dimensional problem. So this is a very straightforward problem I want to show you. You have two springs holding this beam, which is initially horizontal when the load is not applied, this triangular type of loading. And the springs, you see, they have two different stiffness, right? One is the one to the left is 1,000 kilonewton per meter, or I'm sorry, 1,000 newton per meter, and the other one is 1.5, which is like 1,500 newtons per meter. So the as I said, the beam is initially horizontal, and the springs in on deform. And then when we load the we apply the load here, 600 newton meter, which I'm going to actually change it to a just concentrated load. So you have to find the area of the triangle. So half base, 3 meters by the height, right? So that's going to be 900 newtons. So I'm going to put this 900 newtons. Where the centroid of triangle is, the right triangle. 1/3 from the right angle side and 2/3 from the other side. So 2/3 of 3 meters is 2 meters. So I can place that as a 900 newtons right there. So you guys know that any distributed load can be replaced by a concentrated load where the magnitude of that load is equal to the area of the load, and that will go right through the centroid. So what we are trying to determine is, after this load is applied, what is the angle of tilt of the beam? So clearly, point C is going to be stretched due to the force because of the spring differently than point D. So that's going to create some rotation, and that's what we're trying to determine. So I call that angle theta. That's what I'm looking for. All right, let's draw a free body diagram. So as I said, very straightforward problem. So we have the tension or the force here in this spring, call it F sub C. And similarly, F sub D here, right? And I can easily figure out what these forces are by just either take moment about C or moment about D. Let's say if I take moment about C and set it equal to 0. Remember, for 2D problems, right, we have 3 equations that we can use, right? Notice that this equation is useless because we don't have any forces in the x direction. All the forces are in the y direction. And of course, we can use our moment equation and balance the forces in the y direction. So normally we have 3 equations, but only 2 equations are going to be used here. All right, so let's go ahead and take moment about C. So that gives us moment of F sub D times 6 would be moment about C. And then the 900 coming from the triangular, that's going clockwise times 2. So the moment of F sub D is going counterclockwise positive according to the direction I picked here. The moment of the 900 is going to be clockwise. So we solve for F sub D. That becomes 300 newtons. And then just by inspection, guys, if the force at D is 300 and you have 900 here, so F sub C clearly has to be 600, right? Balancing the forces in the y direction, F sub C plus F sub D minus 900 equal to 0. So if this guy is 300, F sub C has to be 600. So at this point, we'll just say, okay, the spring at C, or the force of the spring, is what? K times S, right? For a linear spring. So for C, which the force is 600, right? We can determine the amount of deformation. So S sub C is force of C divided by its K. Be careful, there are 2 different Ks here. So K at C, or the spring there, is 1,000, be careful with the unit, 1,000 newtons per meter, and then the force that we just calculated is 600. So we don't even need a calculator here. So this becomes 0.6 meters. So that's how much C is going to stretch and move down. And similarly at D, same thing, different K. Be careful with that. So force at D, we calculated to be 300, but the K is 1.5 or 1500. 1.5 kilonewton meters or 1500 newtons per meter. So this becomes 1/5, which is 0.2. So look, guys, this beam was initially horizontal, right? Right, better. So initially horizontal. So point C is going to move 0.6. I'm kind of exaggerating because remember, this whole thing is 6 meters, right? See, the beam is 6 meters long. And this point D, is going to move only 0.2, right? So this is 0.6, and this is 0.2, right? So this is going to rotate. So this is how it's going to tilt. So basically, we're trying to find this angle here. See this angle, which is going to be very small because, as I said, I'm exaggerating here. So I think you can go with tangent if you want because the angle is so small, or sine. Maybe logically you should use sine. Sine of this angle, right? Sine theta is opposite. So that would be 0.4, right? And divided by hypotenuse, which is 6, right? So if you use your calculator, it should be about 3.8 degrees, which is relatively small. All right, guys, thank you for watching and listening. As always, I appreciate if you like the video and join my channel. So new problems and more examples. So I'll see you soon. Take care. Bye.